course, Bob is the person in this forum who really needs no introduction, but he's going to get one nonetheless. Bob Wald is the Charles Swift Distinguished Service Professor at University of Chicago. His research is, of course, in a broad range of problems in classical and quantum gravity, including 50 years of black hole thermodynamics. We can say that Bob literally wrote the book. And if you want proof, I have mine here. Note binding, note duct tape on binding. David asked me once, why don't I use my nice pristine copy that's in my office? And I'm like, well, of course, this is full of annotations. So there you go. All right. I'd like to pass the screen over now to Bob. So,
sorry, should I go?
You should go.
Then you'll introduce Gautam.
I'll go on because everybody would forget. But
yeah. Okay, so let me screen share and confirm that that's all visible, and then I will start. So what Gautam and I are going to tell you about, well, it goes under the title of Black Holes Are Watching You. That's the title we used. I think you'll see that it's appropriate, but this was not motivated by some surge of paranoia that we had about black holes. It was motivated by trying to understand better interplays between quantum mechanics and gravity, and in particular, investigating and analyzing issues involved with what happens when you put a superposition, try to make a quantum coherent superposition of a massive body. I mean, you have some particle with mass and you put it through a Stern-Gerlach apparatus or whatever and put it into spatially separated components, and issues with regard to maintaining the coherence, the quantum coherence of those components. So what I'm gonna do in my part of the talk is give you some of the motivation in the original analysis that didn't involve black holes, but it's the analysis of a Gedanken experiment, which if I explain it to you properly, will sound rather paradoxical. But that then led directly, that's the full analysis of the Gedanken experiment is in these first two references. And then I'll turn it over to Gautam to tell you about how the mere presence of a black hole, when you have a quantum superposition, will decohere that superposition on its own. That's the black holes are watching you. Okay, so let me tell you about this Gedanken experiment, which was originally proposed about 5 or 6 years ago by Mari Giovannetti and De Palma. And there's both, while we were initially interested in the gravitational version, there's equally, an electromagnetic version to which the discussion equally applies to. And since the electromagnetic one is probably going to be much more familiar, that's what I'm going to focus on. And I believe that's what Gautam is going to focus on. So like any good quantum Gedanken experiment, this has an Alice in it and a Bob in it. The Bob definitely is not me, because you require skilled experimentalists for both of these, particularly Alice. But Alice has some particle under her control. It doesn't have to be an elementary particle. It could be a nanoparticle, which she puts through a Stern-Gerlach apparatus to put it in a superposition. And in order to check the coherence of the superposition, it's convenient to imagine that this particle has spin, and it has initial spin in the x direction. It goes into a Z Stern-Gerlach apparatus, so it's in a 50-50 superposition of spin up and spin down. Bob, at early times, he has a particle as well that he keeps in a trap, so it's quite out of trouble and not getting entangled with anything. But beginning at time t equals 0 and ending at a time ta later, Alice puts her particle through a reversing Stern-Gerlach apparatus and tries to determines its coherence by measuring its x spin. If it remained coherent when it gets put back together, it would go exactly in the x direction. If it didn't maintain coherence, it would go in the minus x direction sometimes when she measures it. They'd have to repeat this many times to have, complete certainty about what happened in terms of the decoherence. But again, we can do this. But at the same time that Alice is doing this reversing Stern-Gerlach and coherence experiment, Bob is trying to figure out which path Alice's particle took by releasing his particle and seeing whether the Coulomb field or Newtonian field is stronger or weaker, depending on which path Alice's particle took. And the question is, if they do this within a light travel time of each other, will Alice's superposition remain coherent? So let me give you a picture of that, because that was probably hard to follow in words. So this is a space-time diagram of what I've just been telling you about, with time going upward and this z direction horizontal. And Alice, sometime in the past, put her particle in this coherent superposition of spin up and spin down. And then she brings the particle components back together again and determines the coherence back up here. Whereas Bob over here releases his particle, and if Alice's path went this way, there's a stronger Coulomb or Newtonian attraction, so his particle will end up here. Otherwise, it'll be a weaker attraction. His particle will end up here, so he can get some which path information. And the question is, does Bob destroy the coherence of Alice's particle or not? That's a bit of a paradox, because if Bob gets which path information, the coherence can't be maintained. If Bob can figure out which path Alice's particle took, then he's measured where the particle is effectively, and there can't be coherence. But if Bob is doing this at space-like separation, by causality, he can't influence the coherence of Alice's particle. So it's really a very neat Gedanken experiment. And to resolve it, we have to look at the fundamental limitation Alice has on maintaining the coherence, right? There's no black hole in the game now. That'll be in Gautam's portion of the talk, and I'll lead up to that in a minute. But we have to ask, is there some reason Alice couldn't maintain coherence? Well, of course, normally there'll be all sorts of environmental effects in Alice's lab, but she's a superb experimentalist and she gets rid of all them. But there remains a fundamental limit on the coherence of Alice's particle, which is she cannot avoid emitting some electromagnetic radiation if these are charged particles and she brings them together, or gravitational radiation if this is a massive particle and she brings them together. It's just one particle separated into two components. And it's not difficult in the electromagnetic case. It's not difficult in the gravitational case either, but I'll refer you to those papers to look at that, to estimate the decoherence due to radiation. Because we have the Larmor formula Alice is closing a dipole here and reducing this effective dipole to 0 here. It's easier to think about it if you imagine one of these paths is inertial and the other one accelerates to get back to it. So the Larmor formula tells you that this is going to be the 1 over r part of the electric field, the dipole over the second time derivative of the dipole moment. So this then is an estimate of the power being radiated to infinity. This is an estimate of the total energy radiated, but that will come off in photons of frequency 1 over Ta. So this is going to be this dipole moment over the time. I'm working in units where h bar and c are 1. This thing squared is going to be an estimate of the number of entangling photons that Alice emits when she recombines her particle. Well, if this is greater than 1, that means that Alice's particle is going to be entangled with emitted radiation, and she's going to have destroyed the coherence of her particle completely on her own, independently of what happens with Bob. So she's going to have to do it in such a way that this number is small. But if she does that in such a way that that number is small, then Bob, in order to do his experiment, his measurement within a light travel time of Alice's experiment, as shown here in the protocol, he has to be in this wedge here. If Alice takes her time or has a weak dipole, Bob has to be far away or do it quickly or deal with a very weak dipole moment. And we showed the analysis is quite interesting in itself, and it has some interesting twists, but vacuum fluctuations limit Bob's ability to get which path information, and he can get negligible which path information in this situation. Okay, well, this discussion is mainly to put you in the mood for what I'm about to turn over to Gautam to tell you, because there's an interesting twist on this if a black hole is present. If a black hole is present, well, Gautam will have the space-time diagrams, but the black hole, what's inside the black hole never is going to causally influence Alice. And Dane Danielson, another of my students, co-author on these papers, asked the question a year ago, well, what if we have a black hole and Bob performs his measurements inside a black hole? Well, of course, Bob's going to fall into the singularity, but we can consider Bob's to be expendable. I'm not one of them, so I won't object, and have a whole sequence of Bobs. They're not going to causally influence Alice then, but now we have a lot of time to make measurements. So even if Alice does this very slowly, these Bobs can gather which path information. They can't come out and report it, but they can gather it, and that's going to be enough to imply that there must be decoherence. Well, but Bob's measurements can't be relevant to Alice's experiment, so it would seem that the black hole itself must be harvesting which path information. And this is the point where I'll turn it over to Gautam to explain that remarkably that actually is the case, and one can analyze it and, well, see that it's actually very soft photons or gravitons that the black hole is harvesting. But let me end here and turn it over to Gautam.
Well, we're probably all thinking that it's too bad we can't ask questions, but I'm going to follow the rules and not ask a question yet. But I do have a little introduction for Gautam. So Gautam's work is also, unsurprisingly, in the general areas of theoretical and observational quantum gravity and quantum gravity, including gravitational memory, infrared finite scattering, and this black holes and coherence, quantum mechanical coherence or decoherence work that we're going to hear about in a minute. Gautam is currently at the Princeton Gravity Initiative. He did his PhD with Bob Wald at University of Chicago. And before that, he was at UMass Amherst as an undergraduate, which is where I met Gautam. And yeah, it's great to see you come back and give a talk. All right, so I turn over the screen to you.
Okay, can everyone hear me and you can see my screen and everything? Yep. Okay, well, so thanks to the organizers and also thanks to Bob for giving such a nice, introduction to what we did and what I'm about to talk about. So I won't give any of this introductory or this title slide because Bob already mentioned some of the work. Okay, so I'm going to take one slide and just also just restate some of the points that Bob just made, maybe with some more space-time diagrams and also slightly more quantitatively estimate this decoherence so that we can see how to calculate things in the black hole case. So, and also I'll restate the lessons that Bob hopefully just impressed upon you, which is that the causal consistency of the theory, so in QED or in this linearized quantum gravity, implies that Alice's quantum superposition, which I'll denote by what Bob was showing before, which is that Alice has some wave function A1 with spin up, with her particle going to the left, or spin down, and I'll denote the wave function of the particle going to the right as A2, and she has initially a coherent superposition of her particle having gone to the left or going to the right. And when she tries to recombine that particle, to check for its quantum coherence, she has to decohere herself at least as much as any Bobs could possibly measure her at space-like separation. So that's what Bob estimated and showed you. That's what we generally proved in our more, rigorous analysis, not using these kind of back of the envelope methods, but that's what we proved in that case. And so that really means that, well, this is the causal diagram of Alice doing the experiment and Bob sitting here at space-like separation. And this, when Alice is doing the recombination, we have this Bob over here trying to make a measurement. And what Bob Wald was trying to mention trying to explain was that when Alice does this recombination, she's got to recombine, her decoherence has to be consistent with the possibility of any number of Bobs, not just one, but any number of Bobs trying to make measurements at space-like separation. So that's what we generally proved, and this is the kind of space-time diagram. I won't go over, since I'm talking to the DGRAV community, I won't go over these space-time diagrams in too much detail, but it's hopefully, null infinity is going to play some role in this talk, as well as time-like infinity and others, but those, I won't go through too much detail. Feel free to, I guess, review that in the question period or something if anyone's confused. But this is the kind of diagram or the kind of separation and recombination I want you to have in mind. And so that means that Alice has to be decohered even in the absence of Bob, as Bob Wald was mentioning. And that means that, well, in particular, Alice is decohered by the radiation she emits, which must emit, some which path information. And in flat space-time, well, she doesn't really, decohere herself when she holds this superposition static. So what Bob was estimating was the amount of decoherence attributable due to the fact that she was recombining this experiment, this superposition within a light travel time from Bob. And then during that time, she might radiate over that time, TA, and we need to estimate that in order to determine the, which path she went on. So if one wants to calculate that, the way to do that, is to kind of go to infinity and just collect the radiation that she, emits during this process. Now she has to decohere herself in the absence of Bob. So I've neglected to even draw Bob in this diagram because he's irrelevant for the amount of decoherence that Alice emits or produces. And if I look at, if I write down the asymptotic state of what Alice's particle is, it's just useful to do so to collect all the radiation. So this is the radiation of Alice's particle having gone to the left. This is the radiation field of Alice's particle having gone to the right. These are both radiation states at null infinity. And when Alice recombines the particle, at any time after she recombines, she can check for the coherence of the particle by measuring, for example, the spin of her particle. If it's in a coherent superposition of spin up and spin down in the z direction, she'll always see, spin up in the x direction. But she could, if she lost coherence by radiating some which path information, see spin down in the x direction. So the way to estimate or the way to calculate her decoherence is to compute, the orthogonality of the radiation states of her particle having gone to the right and having gone to the left. And one way of stating what Bob was mentioning in his talk was that if Alice recombines this particle slowly enough, and and Bob estimated particularly how slowly she needs to do it. She's really closing this dipole, so she has to do this slower than the kind of time scale, associated to this dipole. Then she can ensure that the radiation states are the vacuum state at null infinity, and you can compute the the degree of decoherence. Well, obviously, if it's the vacuum state, then we can already calculate it and see that the decoherence is 0. One other way of calculating it is to compute the expected number of photons emitted in the difference state. So I take the difference of the radiation states of Alice going to the right and Alice going to the left. If you compute the expected number of photons, well, again, that's going to be 0 if it's the vacuum state, but this formula is going to be useful for later in this talk. And if Alice had done the experiment not optimally, if she had radiated an order 1 number of entangling photons, then she would have been decohered. But the main message of this slide is that if she does this experiment slowly enough, then she can ensure that she's absolutely, she can do this experiment in such a way that she absolutely maintains coherence. The decoherence is effectively 0. Okay, so now getting to what Bob posed at the end of his slide and what Dane suggested about a year ago, which was, well, what if Alice is in the vicinity of a black hole? And, and as Bob was mentioning, we could start putting bobs in the interior of the black hole, and they could, in principle, gather some which path information. So now what we're going to show is by doing a similar calculation as the one I just kind of outlined for you here, but in the presence of a black hole, we're going to show that a black hole, the presence of a black hole inflicts a fundamental rate of decoherence of any quantum superposition in its exterior. And in particular, a black hole basically harvests which path information and destroys the coherence of the superposition in a finite time. Okay, so let me again just give you the space-time diagram, but now this is for Alice's experiment outside of the black hole. Note, I've neglected to draw Bob in this. I guess in a slide or so, I'll reinforce the point of why Alice needs to be decohered, but it should be absolutely irrelevant for this calculation, and we're just going to calculate everything in the exterior of the black hole. And this is the Penrose diagram of a black hole formed from gravitational collapse. This is the collapsing star. That's not going to be relevant till the end of the talk when we discuss, how to compute the coherence and in what vacuum state and so on and so forth. This is the singularity. This is just meant to remind you that it's a black hole. That's also not going to play any role in this talk. This is the horizon. That's going to play a really big role in this talk. Well, this is null infinity, as I said before, and Alice is doing this experiment outside a black hole. So the first thing I need to say is that Alice better not fall into the black hole. So she's going to maintain some fixed proper distance from the horizon of the black hole. She's got to have some, accelerate her lab or something. At the same time, her particle, she's the one, her particle to fall in towards the black hole and radiate. So she's going to accelerate her particle in such a way that it maintains as close as possible to the killing, time-like killing field outside the black hole as close to static as she can possibly make it. Of course, she's got to separate it, hold it, and recombine it, but we're going to make her do the separation and the recombination as slowly as you'd like. And I'll mention how slowly I really need it to be, but it's going to be as slowly as I like to ensure that I don't radiate, neither path radiates anything to null infinity. And we're going to hold this superposition outside of a black hole for this particular proper time T in Alice's lab. So TA was the recombination time that appeared in Bob's talk. That's not going to be very important for this because we're going to make sure that she does the recombination very, very slowly. But what we'll see is this time T of just holding the superposition outside the black hole is going to make all the difference. That's going to really, cause this decoherence. Okay, so this is the experiment. Alice is kind of sitting outside a black hole. And as I mentioned before, the idea or the way we came to this conclusion or, thought that this might be true is because, again, you could put the bobs on the inside of the black hole and try to gather some witch path information. So in some sense, Alice must be decohered on her own as if there was bobs in the interior. Okay, and just to, now let's start doing a calculation. So we're doing this separation, holding the particle outside the superposition outside the black hole for time t, and the recombination arbitrarily slowly. So we're going to require that, in particular, that Alice does it slow enough, well, slower as compared to this dipole timescale. Also, she's like, bringing her particle through some gravitational potential now. She's got to make sure she does it slower than that, timescale associated to that. Well, we're going to assume that Alice can do that. She's a really, really good experimentalist. She's doing this as optimally as you'd like, and she's going to ensure that she radiates negligible radiation to infinity. However, now we're going to show that no matter how optimally Alice does the experiment outside the black hole, she cannot avoid radiating into the black hole. And in particular, the decoherence cannot be made zero. She cannot avoid radiating witch path information into the black hole. Okay, so let me now explain that point. And in order to do so, I need to just quickly review some, black hole geometry. So it'll be actually useful to not use a Penrose diagram, but, it's really hard to draw angles on a Penrose diagram. So so this is the black hole. Again, as before, the cross sections of the black hole are spheres. The time along the black hole is what I'll denote as affine time. It's related up to a redshift factor, which is negligible, and we're assuming that Alice is not doing the experiment extremely close to the black hole. The affine time on the horizon of the black hole is related to, this killing time on the horizon, where by this exponential factor. The t here we're going to take to be also the same as the proper time in Alice's lab. Again, they're related by a redshift factor, but we're assuming that Alice is not doing the experiment extremely close to the black hole. And r here is the kind of distance off the horizon of the black hole, the radial distance off the horizon. Okay. And so this is this is the experimental setup. This is exactly what we're doing. And now what I want to do is analyze the radiation field emitted by Alice following one of these, Alice's particle following one of these trajectories. Okay. And so in order to instead of doing a superposition, let's just do kind of the simple problem of, the warm-up problem of just simply displacing a single charged particle outside of a black hole. So what am I doing? Let's just do the warm-up problem of we have a particle initially at some distance from the black hole B that's held fixed for some, for forever. And then at some point in time, I'm going to displace it to a new position, B plus D, where we're going to assume that the distance I am doing this experiment from the horizon of the black hole is much bigger than the amount that I'm displacing it. So I'm just displacing it to a nearby, stationary trajectory. So here's the picture. I have a particle outside the black hole. I'm going to then slowly displace it to a new position, which is this R equals B plus D. And all I want to know is what is the radiation field emitted by this particle? Well, if I do this displacement very, very slowly, I can ensure that I radiate basically nothing to null infinity. But what I want to know is what is the radiation state on the horizon of the black hole? So in order to do that, in order to analyze the radiation field on the horizon, we need Maxwell's equations. And Maxwell's equations actually takes a very simple form on the horizon of a black hole. It's, this expression here where it relates what's the so-called Coulombic field, which is the radial component of the electric field on the horizon, to the horizon radiation. So this is the horizon radiation because, radiation is oscillating transverse to the direction, of motion. So it's gonna have angular components on the horizon of the black hole if it's radially, falling into the black hole. So that's what the angular component of the electric field is kind of telling you. And the radial component, the reason it's the Coulomb field or the Coulombic data is because, well, for example, if I just have a static test charge outside of a black hole, one can just straightforwardly verify that the angular component of the electric field on the horizon vanishes, whereas the radial component is non-zero. So what is that saying? That's saying that if I have a static test charge, it doesn't radiate into the black hole at all, and it just registers some radial component of the electric field, which corresponds to what you would have guessed. It's basically the charge of the body divided by the distance squared, from the horizon of the black hole. Okay. So that means, if I initially have this body here over here, that means that I'm registering some radial component of the electric field here. And then I'm going to slowly move the body to a new position. And I'm going to get a new radial component of the electric field on the horizon because I've changed the position of the body. It's kind of a trivial statement here. What does that mean? Well, throughout this displacement, if I'm doing this very, very slowly, the time derivative of this change is going to be very small, which means that the magnitude of the electric field is very small, but you cannot set the electric field to zero on the horizon or approximate it to be zero. Why is that? Well, the change in the radial component on the horizon of the black hole is non-zero. The change in the Coulomb field on the horizon is non-zero in this process. I'm moving a body from one position away from the horizon to a new position away from the horizon. And so if I integrate this expression, that means that if the change in the Coulomb field on the horizon is non-zero, that means that the total integral of the electric field, the horizon radiation, cannot be zero. It cannot be zero on the horizon. Okay. So what does that mean? Well, that's not necessarily a big deal or going to give you a bunch of decoherence or imply any of the statements that I've been making in this talk, except for the fact that if you write the electric field in terms of the vector potential on the horizon, the electric field is the time derivative of the vector potential. And so if I plug that into this expression, what does that imply? That means that the vector potential must suffer a permanent change between early and late times due to simply moving a body outside of a black hole. Okay, so let me give you a picture so that you can follow along. So what am I saying? I'm saying that if I have a particle outside of a black hole and I slowly displace it to a new position, the vector potential on the horizon of that black hole must suffer a permanent change between early and late times. The size of the permanent change is proportional to the change in the Coulomb field registered on the horizon of the black hole. Okay, and so if the change in the Coulomb field is non-zero, that means that the change in the vector potential is non-zero on the horizon. Again, that's not so like a cause for alarm at this point. You shouldn't be necessarily concluding that this is going to give rise to the claims I've been making, except for now we can just directly compute the number of photons emitted due to this process. So how do we do that? Well, so in order to compute the number of horizon photons on the black hole due to this, process of moving the particle outside the black hole, we need to quantize the electromagnetic field. Okay, and so this is maybe the most, so everything I've been saying now is fairly straightforward and trivial. This is maybe the more complicated bullet point of this slide. So in order to quantize the electromagnetic field, you need to choose a vacuum state. I want to know how many photons have I emitted. I need to tell you, well, what is the state of 0 photons? For a black hole formed from gravitational collapse, the natural vacuum state is the so-called Unruh vacuum. So that's not so easy to specify on the horizon of a black hole, if for those of you familiar with the Unruh vacuum. However, at low frequencies, and we really are working at very low frequencies, we have to make sure Alice's protocol is done very, very slowly to avoid emitting any radiation to infinity. The Unruh vacuum is equivalent to the more, familiar, maybe to some of you, but definitely easier to work with on the horizon of the Hartle-Hawking vacuum. Okay, so if that was confusing at all, the upshot of that statement is really that I can compute the number of photons in the Hartle-Hawking vacuum to estimate the amount of photons emitted by during this process. And the reason why that's very nice is because the Hilbert space of the Hartle-Hawking vacuum can be exactly described on the horizon of the black hole. And the Hilbert space, well, has an inner product, and in particular then a norm on the space of vector potentials on the horizon. So all of this is to say is that, the quantum field can be now specified purely on the horizon of the black hole, and I can tell you what, in particular, the inner product or norm is of any vector potential that we wish to quantize. Okay, so this formula, it's not so important that you remember all of the details of this formula. The key thing is that it depends on the Fourier transform of the vector potential on the horizon. It has this factor of omega, the frequency, and this is Fourier transform with respect to affine time, and it's an integral over positive frequencies and an integral over angles. And the reason I want to write down this formula for you is because if I give you a classical vector potential on the horizon, the quantum state of that is a so-called coherent state. And the expected number of photons is of any coherent state is simply the norm of the classical vector potential that I use, to create that state. So what am I saying? If I want to compute the number of photons associated to some field, some classical solution, I just need to compute its norm, and I can compute that norm directly on the horizon of the black hole. Okay, so that, well, hopefully everyone followed that. I mean, all I'm saying here is that I want to know the number of photons, and I just have to plug in the, that step function like behavior I gave you before into that formula, into this formula to compute the number of photons emitted. And we're nearly then done here. So if we have a classical solution that corresponds to this permanent change between early and late times, that is, you have to have if you're changing the Coulomb field on the horizon, then the Fourier transform must diverge like, the Fourier transform of a step function basically at low frequency. So it must diverge like 1 over the frequency. And if we compute the number of photons emitted in this process into the black hole, again, nothing is emitted to infinity. We've done this process as slowly as you'd like, but the number of photons emitted into the black hole is logarithmically divergent at low frequencies. And so what is the upshot of this analysis? Well, displacing a charge outside of a black hole and keeping it there forever results in an infinite number of soft horizon, well, in this case, photons emitted into the black hole without any emission, well, if I do it slowly enough, any emission of photons to infinity. Okay, so I'm not interested in leaving particles at that position forever. I want to do an actual finite time experiment. But if I then displace the particle after a time t in my lab, then the number of photons will be, if I displace the particle back to its original trajectory after a time t, the number of photons emitted into the black hole will be finite, but it can be very large for large t. And so the way to calculate that, and now I've put in all the factors because we're going to do an estimate in a second, but the number of photons emitted, so now I have a vector potential, let's say I displace a particle for some amount of time t in my lab, which is some amount of affine time on the horizon. I maintain that for some amount of time, and then I bring it back to its original position. That's what the wave, the waveform will look like on the horizon. And if I compute the number of photons, well, the number of photons will be logarithmically divergent in the amount of affine time that I've displaced it. But as I mentioned before, the affine time is exponentially related to the killing time in Alice's, or the proper time in Alice's lab. And as a result, the number of photons is linearly growing in time at some particular rate. That's determined by the amount that I've displaced it, my distance away from the horizon, and the mass of the black hole. So let me finish up here. So now if we do Alice's full experiment, well, let's consider the simple case where Alice keeps one particle inertial forever and then displaces the other one. And it now follows this displaced trajectory that I really have to page back. It follows this displaced trajectory and then later on comes back after a proper time t. Sorry for paging back so much. Okay, so if we do this, so the first trajectory that doesn't, get displaced at all emits no radiation. The second component that goes on this displaced trajectory held for a proper time t and then displaced back emits an expected number of horizon photons proportional to the time it was displaced. And their decoherence is going to be determined by the orthogonality of, well, the vacuum state for Alice not displacing the particle, and the other state, the quantum state corresponding to Alice having displaced the particle. And that's, related to the expected number of photons in this displaced state. And if the expected number of photons, if this displaced trajectory emits an order 1 number of photons, Alice's particle will be completely decohered. And so that means that there is what am I saying? I'm saying that if I create a superposition outside of a black hole and I hold it for a certain amount of time, after a certain time, which is, which we'll denote as TD, the decoherence time, she is decohered. She can then, at some later time, recombine the particle and check for the quantum coherence, but she will have emitted an order 1 number of photons after a certain, particular time that we can now estimate. So if Alice holds a static charge superposition outside of a black hole, after a certain amount of time, she will have emitted an order 1 number of entangling photons into the black hole. And don't start writing proposals to try to measure this effect. It's a very slow rate. Black holes are watching you, but they're, they're, squinting. The decoherence time is, if you had an electron superposed over a meter, and the sun was a black hole, and you were doing this experiment on the Earth, then this was a very slow rate. I mean, it's about 10 to the 43 years. If you checked back and tried to recombine the particle, it'll be completely decohered due to the presence of the black hole. However, if you did this experiment at the ISCO, so at around 6M from the black hole, then the decoherence time is about 5 minutes. The black hole will have completely acquired which path information on the superposition within about 5 minutes. And there's a similar analysis in the gravitational case, but I don't want to go over time too much. So let me just tell you the answer. Well, in the gravitational case where you just create a superposition of a massive body outside of a black hole. Again, the black hole acquires which path information, but now by the Newtonian field of the body having gone to the left or gone to the right. and forces the emission of soft gravitons, a constant rate of soft, well, the number of gravitons is proportional to the time I made the superposition. And after a certain amount of time, the black hole fully acquires which path information. And in this particular example I've given you, it's a very slow rate, but in the example I've given here, I mean, if you take the Earth and put it in a quantum superposition displaced over its own radius, and the sun was a black hole, then it would decohere in about 10 microseconds. And let me just say that it would not be easy. I think this is what we have in our paper. It's not be easy to put the Earth in such superposition. And let me just kind of summarize, what Bob and I are really saying here. So the causal consistency of a quantum superposition gives rise to constraints on its quantum coherence. So this was essential in flat spacetime to understand the resolution to the Gedanken experiment that Bob was describing. And we showed that, this also results in, this new effect of the fact that a long-range fields sourced by these spatial superpositions, they affect the quantum state on the horizon of the black hole and forces the production of entangling radiation into the black hole, requiring, allowing black holes to acquire which path information about quantum superpositions in their vicinity. Eventually, a black hole will decohere any quantum superposition. And this effect is, well, in some work that's now in preparation and hopefully will be out shortly, this effect is really due to the presence of a killing horizon, in Alice's, in the vicinity of Alice's experiment. If Alice performs her experiment sufficiently adiabatically outside of a star, she can always ensure that she emits negligible radiation and maintain the coherence of her particle. And so really as I've hopefully described to you, and hopefully the rates have convinced you, this effect I don't think is of any practical importance. There are current experiments that are trying to make these quantum superpositions and measure coherence of them and, understand properties of quantum gravity. These are not going to be important. This effect is not going to be important for those currently contemplated experiments. But I think trying to understand the consistency of quantum theory in the presence of gravity in the manner that we are describing, leads to interesting insights. And I think this effect, being one of them, is of fundamental importance for our understanding of black holes and horizons in a theory of quantum gravity. So I think with that, I'll take questions and I'll end there.
All right, let's thank both of our speakers. So let me ask for questions. So since I can only see a very small portion of the participants here, well, small enough. Why don't, if people either want to send something through the chat or just unmute yourself and shout it out?
Okay, I'm going to have to say something here. I feel like I have to say something anyway. And it's got to do with radiation. And it's simply this. I see Gautam, that was the name here of the person who was speaking. You described the radiation field, the electromagnetic field at the horizon, at the singularity of space-time that exists around a black hole.
No, well, okay, I'll let you finish, but it's not nowhere near the singularity.
Isn't that where the black hole, isn't that where you were talking about the radiation field?
No, on the horizon of the black hole.
Well, the event horizon of the black hole. That's the singularity in the black hole in space-time.
No.
Yeah. And so maybe I'm not speaking the language that you were talking about it to me, but that's what it sounded like to me, that you said that the radiation field at the singularity of the black hole, if you like, the event horizon, that the field was purely radial. that there were no transverse, there were no other components of the non-radial components of the electromagnetic field were basically zero.
Well, not while the body is moving. It's when the body is stationary outside the black hole, it emits no radiation, and therefore
there's no radiation that passes through that horizon, the event horizon. That's correct. Okay.
Sorry, if I can just interrupt, because I can see the chat. So one of the other participants sent a message to the chat, I think trying to clarify that the horizon is a coordinate singularity, and Gautam is mentioning that it's actually not a geometrical or physical singularity. But I believe that you haven't actually finished your question.
No, well, I haven't. I was just describing what he described, I thought, as the electromagnetic field at the event horizon. And he said that it is purely radial, which is true, because the fields, the electromagnetic field is radial is radial at the horizon, and yet electromagnetic radiation is a transverse type of form of radiation of the propagation of the electromagnetic field. So he basically just said that the electromagnetic field doesn't propagate through the event horizon. And if it doesn't propagate through the event horizon, then how can we see any radiation outside the black hole? We don't. That's why we call it a black hole. And so I don't quite see how that's related to coherence, and whatever is going on inside the black hole is not available to us through electromagnetic radiation. And the same goes, by the way, for gravitational radiation. Again, it's a transverse field. So we only see the longitudinal components, but we won't see any radiation, either gravitational or electromagnetic, that passes outside the black hole, just like we can't see into it. It's, it's a kind of a symmetrical thing. And so I'm just trying to understand, since there's no radiation that passes from one to another, and he talked earlier, or it was talked earlier about Bob and Alice's particles. I want to say that Bob's particle is an independent entity compared to Alice's particles, and the only way that Bob can see what Alice's particles do is through radiation. And so it's not through doing another experiment in terms of on his particles. And so I'm a little not really, what I'll say, understanding your total arguments here about this need. The only way he can see Alice's particle is through the radiation that she emits. And I cannot understand the argument that says if she does it slowly enough, if she does these operations, there's no radiation. That's
okay,
I'm
gonna interrupt here for a minute.
Yeah.
I wanted to say that there are a couple of messages in the chat where people are also putting in their point of view.
Oh, I'm glad
or
to hear it.
adding
Sure.
interesting, relevant comments.
Okay.
So I would
Yeah.
say, since time is always ticking. That's what time does.
Yeah. Okay.
Maybe we'll let someone else ask a question.
Okay. Thank you.
Sure. And I certainly have questions, but I want to give other people a chance first. Or, well, let me throw out a question, and maybe that will, then people will be less shy. So I have two effects that were occurring to me during the talk that I was wondering about. First of all, I'm not saying I understood everything in the talk, so I have lots of questions about the steps, but in terms of the framing of the problem, one of the things that I do worry about is using accelerated observers, the ones that are following the killing time, that there's some other source of energy or force that's allowing them to stay on the killing time orbits. So I wonder about, since it's all small effects, taking that into account, how that might change things. The other thing I wonder about, which is at maybe the other end of the spectrum, and especially 50 years of hard thought, that the black hole radiation is happening at the same time. So I was wondering if you had thought about how the black hole radiation might have messed or mixed with this stuff and the timescales involved, your capital T, capital TA, and the black hole radiation timescale.
Okay, those were two very separate questions, but
Yeah.
you don't need extra. I mean, you could build a shell around the black hole and, well, you need to put a counterweight at the opposite end so that you don't mess up the sort of unstable equilibrium, but you could put, it doesn't require any energy to keep Alice's lab stationary, right? She can just put that on a shell or be attached to very far away with the string or whatever. Again, you'd have to anchor the very far away thing somehow, but I would claim there's no problem doing that. The other question is a very good one, and one that Gautam, Dane Danielson, and I have worried about and will be addressed in the paper in the in preparation thing that Gautam is referring to in this on his slide that's still up. So the Hawking radiation will also cause decoherence, but that is a separate effect. And if it's a completely distinct effect, if Alice is reasonably near the black hole, the effect that we're talking about is much more important. If Alice is really far away, then of course, none of these effects are important, but the Hawking temperature doesn't go to zero, so that will eventually dominate these effects that, well, the angular size of the black hole goes to zero too. But anyway, the Hawking radiation effect goes to zero more slowly at infinity than the effect we're talking about. But near the black hole, this effect dominates. Yeah. And and most importantly, it's a completely distinct effect from the Hawking radiation.
Let me also add the Hawking radiation is most efficient at decohering Alice's superposition when the wavelength of the Hawking quanta are of the order of the size of the superposition. So Alice can also do things with her experiment to ensure that she is not going to be decohered by the Hawking quanta, even at any distance, basically, from the horizon. As long as if she's extremely close, then she's really seeing acceleration radiation, and it's a different story. But as long as she's not extremely close, really, really close to the black hole, but not has control over superposition. Basically the statement is that these effects are distinct effects, and there's a huge range of space where this effect that we're describing is actually much more dominant than the kind of thermal radiation emitted by the black hole. But that's a very good question to make sure that we account for all the possible fundamental sources of decoherence.
All right, well, thank you. So I was going to make a suggestion that since we're kind of chatting now, Gautam, why don't you stop sharing screen, then we can see more faces. And also another person has had their hand up, Kartik.
Yes. So in the black hole case, Gautam, you said, you can put a bunch of bobs behind the horizon, but you don't need to. You can just look at the horizon and see what's going on. So in the flat space-time case, when there was an Alice and there was a Bob, if you block out Alice with a causal diamond and then just forget about the Bob, can you see the same effect on a causal diamond?
Well, okay, so the question is, are you restricting me to only consider the fields on the causal diamond, or are you just telling me to ignore Bob?
Just only on the causal diamond. I mean, I'm doing the same thing that you did in the black hole case, where I'm forgetting the Bob and putting a horizon. Now it's a causal diamond kind of horizon, not a killing horizon or event horizon. But can you see that effect directly on the causal diamond?
I think
dealing with Bob.
Yeah, so the answer to your question is, in principle, definitely that must be the case. It's more of a question of practice. Like, you know, in order to calculate things, I was using the fact that the horizon and I was taking the horizon and scry to be a full Cauchy surface in which I specify the full state on, and then I can compute this inner product to determine the degree of decoherence of Alice's particle. So this causal diamond is, not going to be a Cauchy surface for the full space-time, and there's issues related to that. And also, if I restrict the quantum state to just this causal diamond, it won't be a pure state anymore. It'll be a mixed state, the vacuum state. So there are so the answer to the question is definitely it must be possible. But what my calculation or our calculation looks like when you restrict to those subregions of space-time is the steps of the calculation undoubtedly look very different, but the answer must be the same. So that's my answer.
Right. Yeah. So you're saying, yes, we can do it, but it's hard.
Well, I mean, in fact, Gautam, Dane, and I were yesterday discussing, a version of exactly this issue. And
okay.
That was exactly the conclusion. I mean, it's got to be possible in principle to do it. I don't kind of know the tools right away to, do the I mean, it's pretty easy to calculate, number of photons through the horizon or number of photons through null infinity. And it isn't as obvious to have that kind of tool, if we're just working in this one causal diamond, but it must be possible to do that. I mean, I completely agree with exactly what Gautam said.
All right, thank you.
Yep.
I see Tevian also has his hand up.
So, in fact, my question is perhaps a simpler version. Let me rephrase that. Kartik's question is a more precise version of what I was wanting to ask, which is the attribution of this effect to the existence of a killing horizon is capturing the fact that at null infinity, the radial coordinate is infinite. And so your adiabatic process can eliminate the radiation, whereas at the horizon, it's not. And reframing Kartik's question, is it as simple as that? If the issue is whether the radial coordinate or is the behavior of the radial coordinate on, in Kartik's case, the causal diamond?
I mean, you only get the effect that Gautam described with a black hole.
Mm-hmm.
Now, there is certainly a relation to the fact that you're getting an infinite blue shift. Mm-hmm. And if you had a fuzzball-like star with a huge blue shift, you would get a similar effect for some finite time until you could kind of see until your causal diamond would intersect the fuzzball, and then the effect would, instead of continuing to linearly increase with time, would level off. But it's the infinite blue shift that's really the key thing, I would say.
Thank you for that. You couldn't see me nodding my head.
Yeah, but I could see your thumb, so thank you.
Okay. Can I make another comment now, please? I don't know how to raise my hand.
Sure, go ahead.
The thing which is the event horizon around a black hole is a four-dimensional event horizon. It not only involves space, it also involves time. And so when you talk about infinity, you're talking about null infinity, basically. I take that to mean you're talking about the time at the event, at the event horizon that surrounds the black hole. And so I just don't understand quite what you call infinity when you say infinitely removed in space, and with Alice's experiment, infinitely removed, it's infinitely removed because of the event horizon. And the event horizon is in our world, in our space-time, is infinity in terms of space and time. So if she's outside the black hole, that's what that event horizon means. It's an absolute infinity in terms of space and time when you do your integrals and everything else. And so if you integrate over space and you integrate from 0, your position, to infinity, you have a finite expression for that, which is the event horizon, because we know how to calculate, at least in space, what infinity is, and it's the event horizon. And I'm going to even make
Sorry,
another.
Lee, I'm going to interrupt again. We need to keep the questions in the form
Yeah.
of questions in short.
Okay.
It's also, we're 8 minutes over the hour, which isn't a lot.
Yeah,
Let me just ask if anyone else has some questions or
okay. Yeah.
comments, and then if not, maybe we'll wrap up. All right, well then, that was very interesting and fun for me. Anyways, I hope Bob and Gautam had some fun.
Yeah.
Yeah.
Let's see. So let's thank our speakers again, those of you that can physically clap, or and those of you who are fast and can put your little hands on the screen, that's good. And I'll end the meeting now, say goodbye. So.
Okay. Well, Bob, are you you're the one that's running the meeting here?
No.
Oh,
No,
Any-
I'm
sorry.
sorry.
I'm running the meeting.
Oh. Well,
And I think that continue the conversation via, one-on-one emails.
yes, I would, but I
Fine,
don't know
but-
your email address.
I think that the emails are pretty easy to find if you just go on the web and look for our
Okay.
names. All right,
Okay.
everybody take care and
Okay.
have a good rest of the day. I guess you're more or less day left depending upon where you are. Bye.
Bye.
I,
Thank you.
Thank you very much, Bob and Gautam.